Well, thank you guys for coming. As you can probably guess, this is one of the largest sessions at Amsterdam, and we're very happy that you took your time to come to our session. So this is actually the second part of a series focused on campus design. It's the ENS 1500 that's led by Jakob. And then this is the second one, ENS 2500. You can read the slide. It says advanced campus network design. So it's going to be very focused on campus. And of course, we can't teach you everything. We can't teach you 40 years of switching. You're not going to walk out of here a CCIE. Sorry about that. What we do want to try and help you with today is the way that you think about network design, the way that you approach network design. And we've called this term min-maxing. So Jakob, what is min-maxing?
Well, first of all, let me ask you, who from you are playing RPG role-play games or Dungeons and Dragons games? Okay, like a half of a room. Good, perfect. So it's a min-maxing is a known term to D&D or RPG players where you are maximizing desirable behaviors while building your character and minimizing, well, obviously undesirable traits. So that's where we're trying to push today to you, like, okay, you can actually reapply the same logic to building your architecture of multi-layer campus.
So my name is Sean Wargo. I'm a principal technical marketing engineer with our Catalyst Switching business unit. I work on ASICs. I work on iOS XE. A few of you I recognize from my session. So happy to be here. Jakob.
Yeah, my name is Jakub Matela. I'm a senior solutions engineer, part of America Sales. Currently, I'm focusing on the strategic financial customers, but campus switching is close to my heart. As I started my career in routine and switching business, so I was focusing on switching for the past 9 years. Now on the year 10 of my journey, I'm more focusing on data center switching. I'm really honored to be here presenting with Sean, and thank you for so many of you dedicating 90 minutes of your really busy schedule during Cisco Live week. We really appreciate your presence, and we're looking forward to the following, 83 minutes ahead of us.
That's so fast.
That was fast. So, important call out when it comes to the administration of the session. As you can see, we've got a full room. We won't be able to take any questions during verbal questions during the presentation. But while I'll be presenting, Sean will be taking the questions on the WebEx room. So if you'll access the Cisco Live app, you can jump into the WebEx room and you can ask the questions instantaneously, and we'll try to respond to them live. While Sean will be presenting, I'll take questions. So, as Sean mentioned, this is the second part of mini-series that we've created during Cisco Live, which is first started with the BRK ENS 1500, this is 2500, and we are capitalizing on the knowledge because this is an advanced session, 2000 level. So we assume that you've got a good understanding of multi-layer campus architecture, and we'll be just building upon the foundations that you have. Who joined me yesterday during 1500? Yeah, good. Thank you very much for trusting us with your time again. So, as you can see by judging by the agenda, we will be not repeating some of the concepts, but we'll be making sure that we'll call out some of the most important concepts of the 1500 basic campus architectures. So, whenever that happens, you'll see in the top right corner the sticker, and that means that we're not going to be spending too much time explaining this concept, but just calling out the most important part and moving forward. So, you may feel like it's busy, but this is the intention. You're on advanced session. So I'll be presenting sections 1 through 4, and then for that time, Sean will be answering your question, and then we'll invite Sean back to the stage to cover best practices and integrations with other places in the network. This is how the complexity map of our session will look like. So we'll be increasing complexity as the time progresses, but we're sure that you'll be able to follow. So around the 42 minute mark, we'll invite Sean back to the stage. For now, thank you very much, Sean.
Thank you, Jakob.
And let's start with the campus design fundamentals. So, fundamentals of fundamentals, let's clear it off the way. First, we have to answer ourselves what campus actually is. And by the way, this is the perfect slide to call out one more organizational thing, or maybe aesthetic thing. We realize that yellow highlight is not the prettiest, especially on a white background, but we did it intentionally. If from all the busy slides you have to focus on one thing, just read the yellow highlighted sentence. At the same time, this is the place where we've already been during BRK NS 1500, but so you'll see that coming on and off throughout the slides. So again, back to the slides, what is campus? Campus is, according to the definition, it's a group of one or more buildings which are surrounding people which are coming to work. So we already know that while designing or thinking about designing campus networks, in the back of our head is like, okay, we have to allow the access to the network, to the IT computer network, to the users and their devices. Campus network is not a data center network, despite the fact that we are using some of the same features, the way that we connect devices, the way that devices are organized, and most importantly, the endpoints that we are connecting within a campus network is much different than in a data center network. Therefore, we cannot apply the same architectural best practices, and that's why it's just quick differentiation between these two. So, in a multi-layer campus architecture, we differentiate three main logical building blocks, always. Campus access, distribution, core. This is known to all of you. When we are cramming more functionalities, logical functions to a single physical box, we could do that. For instance, we could create campus core interconnect, which is core capabilities with edge capabilities, meaning this device is now responsible for connecting to the outer world. We could expand our access layer, we refer to it as an extended access, or we could collapse layers, distribution and core, creating collapsed core. So, quick repetition, I told you that's going to be very brief because we want to move to an advanced part. So once we have the fundamentals of the way, let's focus on the principles which are guiding our architecture. Whatever we are thinking about creating as a multi-layer campus, we have to follow hierarchical design model. What it is? Well, simply you want to have quite clear distinction between access, distribution, and core layers, and that allows you to scale your architecture very easily, because if your company that you work for is thriving, it's really easy for you to add another core layer and add to it distribution layer, therefore expanding your network without disrupting or causing any disruption to an existing part of the network and its users. At the same time, we are achieving clear demarcation of fault domains because we are able to clearly isolate separate parts of a network. So it's just a thought, but hierarchical orders really work in your favor. So, quick summary of the principles that are guiding multi-layer campus architecture. We are always using the hierarchical build. Each layer has its specific role. We are building of the building blocks, logical building blocks, which are created of the multiple physical devices. This way, we are creating small fault domains, clear demarcations of the responsibilities. And that also allows us to easily troubleshoot problems in a network, because when we know where the problem occurs, it's really easy to troubleshoot and find the fault. So hopefully at the end of this 2 breakout long mini-series during Cisco Live, you will be equipped with all the knowledge to build beautiful networks of building blocks like the following. And whenever you come across the problems or problematic designs, you'll be able to spot them and quickly fix them. And some of you I see are laughing because, yeah, this is a real life. We've been there, we've seen that. So, now, on to the min-maxing part. As I mentioned at the very start, we thought about building architecture, network architecture, just like building the RPG character. It's very similar because you have limited amount of points that you can spend on certain traits, and you have to build towards desired outcome. So it's the same as building the campus network. The budget is fixed. Usually you don't have unlimited budget, and each layer, in our case, invests in different capabilities, right? So our RPG character is actually our campus network made of access, distribution, and layers, and core layers. Each layer has 6 different skill categories, and they're repeatable. And if you go to cisco.com and open any Cat9K platform, you'll see that we are posting the same scale categories, but the numbers are different because each platform multiplies different or leverages different skill categories. So we thought like, okay, we'll give you 60 points to use because we cannot give you enough points to max out every single aspect of every single skill domain. Why? Well, because this is not how the world works. We usually have a limited budget. So that's why you can assign only 1 to 5 skill points per skill category. So total number that could allow you to max it across the board would be 90. So 3 tiers times 6 skills times 5 maximum points. That 90. We thought, okay, we'll cut 30 off just for the abstraction, just to make it real. So what actually is packed inside each and every skill category? Scale, that's very obvious. You're looking at how many MAC addresses can you actually register in your on your device. What's the layer 2, layer 3 routing scale for you? Speed, well, throughput and bandwidth, basically. So how many ports of certain speed you offer as a downlinks, how much simultaneously you can push to the upper layers. Resiliency, what are the resiliency mechanisms, both on architecture, hardware, and software, and how quickly you can reconverge your network upon failure taking place. Policy and services, it's basically segmentation. Number of VLANs or more sophisticated features like secure group tags that you can support, and also associated services with that. Then, operational simplicity, how easily I am able to operate my network and troubleshoot should a failure happen. Management platform, well, we know that the more devices you have in a network, there is a bigger need for some sort of management platform, which is usually behind the higher licensing level. So this is where the category of the operational simplicity stands for, and power and physical, simple. If I have to invest in a big, powerful box, that's going to cost me more than a small and not so powerful. So, on to our first mission, and we all build a character depending on what kind of a mission we have or the scenario we are up against. So in this case, let's just use our imagination, and your boss told you to create a 3-layer campus network for high-density office, and core has to have edge capabilities, so we're cramming more on the edge. How would you distribute the points? Well, we thought that it would look like that. And at first, of course, it's everything's abstraction, so we just want to drive the point that which parts of the networks or the elements that are creating or influencing the selection of a certain platform should you take into consideration while planning the network design. So for the high-density office, we obviously will invest highly in the power and policy, and this is what we're looking at. We are maxing out power and policy at the axis. At the same time, distribution will absorb the complexity, and core just maximizes determinism. That's why we've got the resiliency and convergence maxed out. So this is the first example of how we should think about planning the network, and it will all make sense because we'll go through examples of platforms that you should choose depending on the situation in each access, distribution, and core layers. By the way, whenever there is this symbol in max min in the top right corner, that means that we are selling you some kind of a min-maxing strategy tip that you could leverage later. So let's clear the table again. Now you know the drill. How would you design the network that would serve large manufacturing plant with the OT-focused campus? I'll give you a second to think. What we know, in a manufacturing plant, traffic is mostly machine-to-machine. Therefore, we're not looking at a high bandwidth, but we need to have predictable flows. At the same time, we have very high availability requirements from the network. We expect the device will live long because we don't want to touch them. Why? Well, because changes are rare and outages are very expensive. So we thought, well, designing such network would require us to distribute the skill points in a totally different way. How? Look at the access. At first, it might look like it's exactly the same as the previous scenario, but we already know that it's mostly signaling rather than bandwidth heavy traffic. That's why we don't invest in the throughput and bandwidth. We focus on resiliency and convergence and power and physical, because often we have to pay extra for specially ruggedized switches, and this comes with the price. The same core focuses on determinism and uptime. So whenever failure occurs, we need to run some very efficient routing protocol that will route around the problem. So this is just a comparison back and forth how it looks between the high density office and large manufacturing plant. And to all my fellow D&D players, you know that every now and then during the scenario, the special event or side quest takes place, where you can actually, upon successful finishing the quest, you can gain additional skill points and further develop your character towards desired outcomes. And such special event or side quest actually took place in an IT world because AI arrived. And even though all the love is given to data center and compute teams, networking team also have a little bit of love, right? Because your boss might have asked you, well, you know, there's this AI motion and we have to invest a little. Maybe we should put the compute somewhere in the core. How would you add this extra points, which is basically extra budget? Where would you invest to capitalize on compute edge connected to the core? Well, the answer is quite obvious. If we are to design high-density office where with added edge at the compute edge at the core, then, well, obviously we need to invest in throughput and bandwidth, or mainly the bandwidth control, as well as the policy and services at the core. Maybe somewhere at the access, depending on where the users of given AI model would be sitting. But what we know about the AI models, they are very intolerant to jitter and latency or loss of traffic. That's why you need to make sure wherever you connect it, you will be in a full control, and you'll have a lot of throughput, a lot of bandwidth, and a full control of, or you'll be able to policy the traffic or make it flow smoothly and consistently. All right, so now you've got to ask yourself a question: what is my quest? Because it's just an example, it's abstraction, right? But think about it in this way, like you're min-maxing. Every decision has its disadvantages, drawbacks, but you have to maximize the outcomes towards your building your network and minimize the unwanted ones. So now we're going to go through the access, distribution, and core layers, but in an order that, well, you know what the access is, right? Access is the main purpose is to connect users. But what it means to the platform choice, it means that I have to have a solid MAC space, an ARP scale. So likely, if we're talking about many devices and users utilizing application as data center, we have to keep also the oversubscription ratio in reasonable ratio, right? So likely you'll be looking at least 92 or 9300, easy. However, if we're expanding the access layer, where we are extending the number of endpoints that will be connecting of different kinds to our network and likely powering up endpoints, then out of nowhere, our requirements or maybe platform choice is changing, because we might be looking at the small form factor device that will be able to put behind the ATM machine, or a ruggedized device that will go under the floor or over the ceiling in a high wet place or maybe hot place or cold place. Then we are paying extra for ruggedized, i.e. 9300, or maybe small 9200 CX, which has some PoE budget. So again, we're looking at the MAC address space, ARP table scale, but at the same time we are expecting to maximize long life cycle stability of the device. So moving forward to the rooted access, maybe you're exploring the idea of enabling Fabric in your network, or just routing from the access. What it means to your network? Well, not only your access layer devices should support layer 2, they should support layer 3. And that forces your money distribution, skill point distribution towards the access scale, towards the access services and policy feature support. That means that you no longer likely are looking at 9200, but you're thinking or leaning towards 93, 9300X, 9350, the new switch that Sean just yesterday was covering during his session, or modular options, 9400. So once you know the drill, the distribution will be quick and a core as well. So classic distribution is just fanning out connectivity to the access and introducing layer 3 to core layer, right? That means that not only we are aggregating all the MAC scale that we are being advertised from the access layer, but also we have to support layer 3 protocols. We're looking at the redundancy, both on the supervisor part, if we're exploring the modularity here, or resiliency, and maybe some kind of the high availability features to be supported by the platform of our choice. That's why we are proposing 9400 if you want modularity, if you want high resiliency, or 9500, 9500X, a pair of them in Stackwise Virtual likely. about which Sean will expand in the second part of this presentation. If we are thinking about, well, we already decided we'll be running extended access and we need to select the distribution, then we have to take up a tremendous amount of the IPv4 and IPv6 route table requirements are growing. We need to have a traffic aggregation, so the support of our uplinks will looking like downlinks at least 25 gig, uplinks at least 100 gig, given that all the endpoints that we're connecting to our networks are actually more and more power and bandwidth hungry. So, collapse campus, we mentioned that whenever you collapse roles, you're not removing logical layer, you're just putting more on a single physical device. Therefore, here we'll be looking at the high layer 2 and layer 3 scale. Then there's non-negotiable that you've got to have a resiliency within the architecture of the platform as well as a software architecture. So we don't expect downtime, and you want to have minimum feature dependency. Therefore, you want to enable as few features to make the functionality work for you, for your design. That's why we are positioning 9600 or 9500X for that role. All right, still with me? Good. Core layer. Core, main goal is simple. High bandwidth, deep buffers, layer 3 transport between whatever's below me to whatever's above me. So we are simply looking at the layer 3 scale here, redundancy of the supervisors, IGP scale, fast convergence, again, no-brainer, 9500s or 9600s on the modular end. For the campus interconnect, where our task is to connect multiple core layers or multiple distribution layers behind them, and we have to distribute the density on other speed, then it's 100 and 400 gig port density, ECMP at the very basic level, or maybe more sophisticated feature support. This is where you will be exploring QSFP Plus or QSFP-DD transceiver support, because you want to have a high bandwidth, but you want to support yourself or have enough bandwidth for the future. So whenever your network will be growing, you want to have this capacity to, if your current platform supports QSFP-DD, you want to be able to grow the bandwidth and support more and more. So 96 and 9500X is your choice. And a core plus edge, so it's even more important. This is a critical part, like centerpiece of your network backbone. That's why you don't want to mess with that part. You need stability, you need predictability. That's why here we are making sure, while selecting the platform, not only platform, but also the iOS XE, the proven software trains will be only deployed at this layer. You just don't want to test beta software on a core interconnect, core and edge, right? That's why 96, again, 9500X, but we are not only looking at the pure scale, but also we are very, very picky and selective on the platform, on the iOS XE version that you're going to deploy. You don't want to have many features, just few that will do the job. All right, we arrive to the services part. And while thinking or architecting services of multi-layer campus, we can think about it in two ways. Through the lens of individual features, or through the lens of behaviors that we want to achieve, or we want our network to behave in a certain way. So if we'll think, or if we'll approach it from a min-maxing perspective, we are looking at the features that are enabling our behaviors. And the behaviors might be different. But even the cheapest network will always give you some sort of availability, deterministic forwarding, segmentation policy, visibility and control. There's no way we could go through every feature available in iOS XE, because there are thousands of them, but we can just talk about the concepts, what you want to achieve and what would be the price of it. So whenever you're thinking about your network, you want to minimize behaviors that really maximize that really matter, minimize complexity that doesn't pay back. Maybe there are two features which are solving the same problem. Maybe I could turn one off. And you want to invest your money where the failure is really of a critical importance. So if we will focus on first two, availability and convergence, as well as the deterministic forwarding, what availability buys you? Basically, you can recover quickly should the failure occur, or you've got a predictable behavior when the failure occurs. So what it means on a basic level, you've got physical redundancy, you've got Ether channels bundling support, you have an ECMP-based network design. For the deterministic forwarding, you want to have a stable throughput whenever the load of the users and endpoints comes or hitting your upper layers. You want to have a graceful behaviors because we cannot forget that the failure will occur. We just want to be prepared for that. So on an essential level, again, this is an abstraction level. Like if we would assign the points, the skill points, the money stakes, you have to equally distribute them to achieve basic level of availability and forwarding. But if you want to take it to the next level, if, for instance, you want to have BFD support, or you're exploring, again, the idea of fabrics, about which Sean will talk more in the second part of the session, then it costs you more. Obviously, you have to spread the money across the table, but that means that not only your distribution and core devices should support layer 3 functionality and reconverge very quickly and be able to support high availability, but also your access and distribution, your access layer devices too. So the min-maxing mindset is like spend money here first in the distribution core, well, but don't forget about the access. Next up, segmentation policy, along with the visibility. Segmentation, obviously, it's a failure containment, but the basic, grouping of the endpoints and users in groups and making sure that they don't talk to each other if they don't have to. While visibility, you have to know what's going on in your network. Every device that you're going to buy off the shelf will give you some sort of visibility. You can log in, type all sorts of show commands, inspect the logs, fine. But when the scale grows, you cannot do it, or it's not scalable, right? So that's why if on a basic level, segmentation policy, visibility, you've got to equally distribute on a minimal level the money stakes that you have. But when you would like to take it to the next level, to the advanced application, then, well, Fabric, for instance, is a great option to extrapolate this physical layer, make sure that you will deploy the overlay designs over the top of the whatever physical infrastructure you have, but it costs money because now you've got to invest in policy and services at the access layer, distribution equally, and you've got to have a scale that supports your plans. Because this is where you could introduce in a policy and segmentation bit, you could invest in SGT, tunneled in a VXLAN tunnel. This is where the policy could be extrapolated from the topology, where no longer IP address matters. And the same works for the visibility and control. If we want to connect a device or group of devices to some sort of management platform like Catalyst Center, usually it requires you to buy a next tier of the licensing, which costs money. So policy and visibility, at the end of the day, are very powerful tools. However, used incorrectly, they can quickly burn through your budget. Then I have two call-outs. One is what we optimize for, especially when we are approaching the, thinking about the services and behaviors within the network, and what we no longer optimize for. So first of all, we want to optimize control plane efficiency. So you want to summarize. These are like obvious things for the advanced network engineers, but we want just to make sure that we reiterate that. You want to form IGP adjacencies wherever they make sense. You don't want to create a full mesh, as we just stated that while looking at the potential fixed platform design. You want to contain failure domain. So if your layer 2 is growing and growing and growing, maybe it's time to rethink the design. And especially you don't want to add layer 2 elements, connect them into the core part of your network. It's undesirable, right? Like when someone proposed that, well, it's a short-term solution which will take down your network. Deterministic layer 2 behavior, spanning tree protocol is here to stay. It's been here for a while, so you have all the toolkit that to keep it tamed, but also to make it work for you, not work against you, right? So you can bundle the links, you can make sure that the forwarding happens where you want it to be, and you're not blocking too many expensive uplinks that you just paid for. And from the entire slide in here, I only highlighted one thing, which is to the access edge discipline, but it tells you disable anything not required for the endpoint connectivity. Well, basically, if you will take it to the next level, it means turning on features is an architectural decision, but turning off features or not enabling them is also an architectural decision. We tend to turn on everything that is available within license, and then our network is hit with a vulnerability that we weren't even aware exists. So what we no longer optimize for. We no longer optimize for complex spanning tree tuning. So if our layer 2 is too big, maybe we should, again, rethink our design. Extensive layer 2 extension, multiple mechanisms that are solving the same problem, like maybe it's worth to invest a little more or turn on BFD, bidirectional forwarding detection, that will inform my upper layer protocols like BGP or SPF faster than their death timers themselves. Therefore, I can achieve faster reconvergence of the upper layer that I really need to be up and running. So some mechanisms are no longer design goals, but there are constraints that we have to eliminate from our network. And again, every enabled service, so you're thinking about the outcomes, the behaviors of your network that you want to achieve through features. So every feature turned on consumes very expensive resources on each and every access distribution core layer device. So again, not enabling service is also an architectural decision you have to think of, especially if you're modernizing your network and maybe it's time to drop the access list, like IP access lists, and replace them with the SGTs. That takes, a long discussion with the segmentation or security team, but it's worth trying and simplifying the network on the way. And now we've arrived to platform. So we talked about the concepts, we talked about like the mindset that you should have, so making sure that whatever you turn on is thought through. And now, what should I choose? Whether should we go all the way for the modular, maybe fixed, what are the differences, and if we will choose this, the modular or chassis type, what are the speeds and feats that we have to think or plan for? Well, as you're well familiar, it's the third day of Cisco Live, so we must have seen this picture multiple times. But we keep expanding Catalyst 9000 family of switches, and the reason is because we trust this is the best choice for you, and we want to give you a flexibility of the choice. However, we need to change or modify the family according to the needs or changing needs of the networking. So, and we are adding across the board both fixed and modular options. Why? Because we believe that the best design takes from the both worlds. Last additions, 9350 with the Silicon One ASIC, and the other side of the spectrum, 9610, also with the Silicon One ASIC. This one, it's 9610 rack unit chassis, but actually there are 2 supervisors and you can load up to 8 line cards, while 9350 is a fixed unit, and both of these are so-called smart switches. But nevertheless, you've got a variety of choice of already existing platforms. So what should you go for, modular or fixed? And some people would say that there's no way the modular doesn't have a place in the current networking nowadays, especially in access. Some will say that the fixed is too limiting. So the rule of thumb is go for the modular if the scale, resiliency, and recovery time are of the most importance for you, and go for the fixed if you want it to keep it simple. But everything that is too simple can actually become very complex over time. So if you decided to build your network only on a pizza boxes, then if you need to add another, well, you're ending up in a full mesh network. What happens if to this site you need to add one more port? You have 48 ports and you need just one more. You have to add another device. Therefore, there's like the IGP churn is just overwhelming. What you could achieve the same in a simple design, just working on the modular chassis. Of course, it's a pros and cons. That's why I believe that the best design and the best architects are actually using the modular and fixed wherever they fit and whenever they see it needed. Cabling then. So we already decided that we're going to use both modular, fixed. What are my options from a link scale perspective, or what should I think of? And before we'll get into 25 and 100 gig, very often at the big companies, the wireless team is separate from a switching team, from routing team, and sometimes the life cycles of each layer are way different depending on the domain, right? So you might be thinking about the access layer refresh, and at the same time, wireless team is thinking about the wireless refresh, or you're thinking about the access layer refresh. So wireless team says, well, we are thinking about Wi-Fi 6E, 7, or maybe what's coming, Wi-Fi 7 next year. And you're okay, I just refreshed my network with high density 1 gig ports. Well, guess what, my friend? You'll be bottlenecking the Wi-Fi 7 and 6E big time. Because if we are even looking at the access point like 9178, this is the biggest access point that we have, but it offers dual ports, not only dual ports, dual multi-gigabit ports, and in order to power it up, you need at least 57 watts. So that means that your port should support UPoE. So if you chose 9200, which limited power over Ethernet capabilities, then you're actually jeopardizing Wi-Fi 7 refresh project that will happen next year in your company. So you have to think about what the next step is and what are the types of the endpoints that we're connecting to into our network. And especially if you're living in a high-density campus used mainly by the wireless endpoints and users, then it means that you have to really invest in a mGig density and power over Ethernet density, because this is what actually modern campus nowadays is. So I like this slide. It's quite a busy slide, but I just want to call out two important things from this and the following, which is very similar. So whenever we're thinking about switching the access distribution and core layers, we have to think about the speeds, but also how the improvements that we're bringing out today how they will impact or how long they will sustain the trail of time. So first thing, whenever we are looking at the SKU numbers and the codes, like 9500-48Y 4C, in the top right corner, you've got the explanation what L, Y, and X stands for. So it's actually easy to decode. 48Y, 48 times 25 gig. What 4C stands for? It's the next slide. C actually stands for 100 gig. So we know that that SKU is actually 48 ports of 25 gig and 4 uplinks of 100 gig. And that goes on and on. It helped me at early days in Cisco to actually decode all these long abbreviations. But what important is, when you're thinking about upgrading the speed of your uplinks between access and distribution, you might want to explore the idea of using dual rate optics. And what dual rate optics are, if you didn't know that, they operate in 2, sometimes even 3 rate optics. So whenever you're upgrading access in the first place because Wi-Fi is pushing you to do that, you might explore adding 10-15% more to go for 25/50 gig uplink supporting optic. Therefore, when you will attempt to refresh distribution, your access is ready, and your distribution downlinks will be upgraded to very high density 50 gig. You don't have to do anything with the access. You pay 10-15% extra, but you don't have to touch the access again next and next and next years. And the same goes between distribution and core, so on and so forth. There are 2 great sessions. I think one of them already took place. So BRK ARC 2098, 2099. Both of these sessions go in depth into access and the distribution core families. So they will go over the next new advancements, both on the architecture as well as the software part. So here it's just a quick math that we run for you, and that will help you to, plan or maybe copy the mathematics behind high-density multi-gig deployment of a 3-tier campus while keeping the oversubscription ratios in check. Okay, features consideration. And we talked about the features, expected behaviors, but what I wanted to call out, there's no way that we're going to go through every individual feature on the list. But the most important is that there are multiple features that you already have running in your network, both IPv4 and IPv6 unicast. And the same story goes through IPv4 and IPv6 multicast. What you really need to think about is like which of them I carry to my new network or which one of them I really need to enable. And what it translates into is actually what kind of a device am I going to choose. Because every endpoint connected into access has a MAC address. And this MAC address has to be registered on the access device, and then it has to, you need to have enough of a MAC capacity on the distribution. So one MAC address equals to one endpoint. That's basic mathematics, right? But if you will inspect cisco.com datasheet of every platform that we have, it usually matches with this mathematics. You'll find that the distribution device tends to support that much of MAC addresses, and it's not taken out of thin air. We just didn't think of, just an abstraction of numbers. We actually run the math on how many on average MAC addresses is registered at the on average access layer device, and how many distribution has to support. The same goes for the IPv6 and layer 3, because each endpoint, each MAC address has one ARP. If it's an IPv6 endpoint, it has at least 3 IPv6 addresses that equals to 3 network neighbor discovery protocols. What does it mean to your distribution? Well, it impacts the scale that you have to support depending on what is the mix, what is the ratio of IPv4 to IPv6. It's a good question. Who actually is exploring or actively deploying IPv6 in their network nowadays? 1, 2, 3, 4. Okay. So you might want to still explore the ARF scale and layer 3 rather than looking at the IPv6 scale. But it builds up because the more you're looking at the core, for instance, and you want to peer with the internet, you want to be able to, your ASIC should be able to peer and accommodate all the layer 3s stored in a public global routing table. And then you've got to do it all, making sure that you have this oversubscription ratio in place. And last thing, if you're exploring the idea of .1x, each authentication has to hold a session from the authenticator all the way to AAA server. And it also costs you resources, and you also have to look at it while planning access layer. So each device, each user, each endpoint has at least one AAA session. IP phone, 2 AAA sessions, 1 for voice, 1 for data, right? So you have to also plan it ahead of time. Last thing that I want to touch, sometimes operations team, again, don't talk to switching or wireless teams. And operations, for instance, plan that you will deploy, or they will deploy ThousandEyes endpoint as an app hosting at every single switch, but they just didn't care to mention that to you. What it means to you as an architect, well, you have to plan ahead of time the resources that it will take, or it will consume of your already overburdened switch at the access, distribution, or core. So one important call out of this busy slide, and those slides are already available within a PDF. So if you haven't seen it, you can download the entire session deck, and we've unhidden many slides. So you'll find it, I hope, interesting. But one last call out is the 9200 is not present in here. So up until now, when you were thinking through your access layer, it was like, yeah, 9200 makes sense. Well, it doesn't if you have an app hosting requirements. Now we've got to just revisit your requirements and revisit your decisions, because every single resource is consumed by the app hosting. So CPU cores, memory, storage, even before we'll turn on any features. So having said that, think about the platform choice, think about the features that you're going to enable, think about the strategy that you're going to take, the behaviors that your network should have before even while drawing your design on a piece of paper. And having said that, I'll invite Sean back on the stage. Thank you very much for the attention so far.
Awesome. All right, so you've made it this far. Now we're going to go into and most of this was covering the best practices for baseline. He used the word baseline a few times. Kind of just a general network design, basic layer 2, basic layer 3. This is going to take you beyond that into areas of things like high availability. I'm going to talk a bit about virtual networking, talk about fabrics, and then additional areas which you may not even be thinking about. Who has a separate wireless team? Your business has a different wireless team. Okay. Your wireless team should be talking to you, and you should be talking to the wireless team, because it will impact your wired design, your switching design. Okay. Similar things with security and other things. So even though these may be considered different areas in your network, they need to be part of your design considerations. Okay. So this is just picking up on that same graph. You're now into the last part. Now, what's interesting here, it's only 2 numbers, but you can see it start to be more drawn out. So we'll spend more time just talking about why those things are important. And then I'll close it out and get you guys back to the next session. So the first part, of course, is high availability. Now, you've built this wonderful network, but it may be mission critical. Now, if you ask someone, do you want high availability? Do you want redundancy? Yes, of course I do. What it usually means is buy more hardware. Okay, either you're going to buy an additional supervisor. Even if you're using link redundancy, it means buying more cables, buying more optics. So if I ask someone, do you want to spend 2 times your money? They're like, I don't know. But using the min-maxing philosophy, it doesn't have to be all one way or all one other way. You can minimize cost in certain areas by maximizing your high availability in other areas, okay? The first part is just like we were doing in the other one. These should be well known to you, so I'll be very brief with them. Talking about, what is HA and what are the areas of HA, then talk about things like SSO and so forth. But then start to really focus on things like equal cost multipath design versus stackwise virtual design, right? And we'll get on then to, it says virtual networking. I did that on purpose because I'm going to use actual fabric terminology. But it's the idea of virtualizing the network. Is there a way that I can maximize my value by moving pieces into different areas and change the way that basic layer 2, layer 3 works, right? And then, like I said, of course, security. And this is going to be a little bit different than the section following, section 6. This is the actual switching security. Okay, so things like 802.1x, things like access control list, and those kind of things that the switch is expected to do. Now, I don't have to read this slide. This is in 1500. The reason I wanted to bring this slide back is just about money, right? And again, the min-max philosophy. And the other piece was the operational expenses versus capital expenses. And this never comes up in the budget meeting when you're talking with your finance team. They're like, could you just buy that 9200? You'll save us like $1 million. Yes, but when we have an outage in this situation that cost us 10 million, I should say euros, but understanding what your cost in the long term will be and being able to actually write that out for the finance team and explain those things, right? Also that high availability is not one thing. It's not just a feature you type in and boom, I have high availability, right? It is many, many different things. It is the topology itself. Is there network redundancy? Is there device redundancy? As well as the things like software upgrades and those things, right? This is a critical decision. We have bugs. Everybody has bugs. There will be new features. There will come a day when you need to do a software upgrade, and that's going to, what impact does that have, okay? Now, at the heart of that, when we talk about device-level redundancy is stateful switchover, SSO, and again, this is in the basic slide, so you should know this. But what's important there is I'm statefully synchronizing all of my MAC addresses, all of my IP routes, all of my access list. Everything that's on that primary control plane is being synchronized. And again, like we have bugs, hardware fails, bad things happen. If that active supervisor dies, I have a duplicate copy on my other supervisor. But it means you bought a second supervisor, right? So you have to convince that finance person, I really, really want to buy this additional supervisor so I can guarantee maybe it's some critical area. Particularly, we were talking about the 9400. Someone was asking me in the chat about a single attached wireless access point. So if that access point only has one cable and that supervisor dies, guess what? All that AP just went offline, okay? And I'll also cover those kind of things. I said, who has a different wireless team? Talk to your wireless team and ask them about how critical their environment is. That may change your design min-max, okay? Now, on the fixed switches, they're fixed switches. They are what they are. But we can stack them together and make them logically into one device. So the same philosophy, and then one of those members of the stack will have this SSO and will become the active control plane. If that switch fails, another switch in the stack will take over. It has a duplicate copy of it, okay? Yeah, and then I have a cool animation that shows that happening. So there you go. But the little min-max philosophy is that, hey, maybe investing extra money, spending my skill points on that extra hardware is going to cost me money right now, CapEx, but it could save us much more money later in OpEx. Now, going through these this slide and the following slide kind of is going to what Jakob was covering with the modular philosophy and fixed philosophy. And they really are philosophy. It's how you wish to min-max your skill points. Okay, so I'm not going to take a religious stance on you should do this, you should do that. It very much is on what is important for that part of the network. Now, when you're looking at modular, it is modular. As the name says, I can change these line cards. It's a grow model, as in you may only need 1 gig or 10 gig today, but 5 years from now, I may move on to 25 gig, 100 gig, and those kind of things. So I don't have to change the actual physical box, right? Plus the SSO and NSF that I was just talking about, it's built into the system. If you buy the 2 supervisors, and it's milliseconds. If the active supervisor fails, it will take over in milliseconds, okay? Now, in addition to that, even at the chassis themselves, and he was talking about the distribution layer or the core, I can combine those distribution core boxes together. So not only this one physical switch, but a second physical switch that goes with it. Now, another one, I said HA is not just a feature that you turn on, but many different things mixed together. Another very important part for your design decisions is power and cooling, okay? So there's also power redundancy. This is actually very common in Europe to have 2 different power feeds. You'll have one electrical power input from one circuit, and you'll have a different power input from a second circuit. So that if the entire power grid fails, you're still getting redundant power from the others. So having enough power supplies to maintain the system. So also, even that, they'll be asking questions about, do you really need this additional power supply? Well, yes, I do, because I have requirements that say I have to support these 2 electrical failures. And then, as I said, software upgrades. This deserves a whole long discussion by itself, but we do patching of the current version that you're on, and I can do in-service software upgrades to another version. People who've been in my session, I talk about ISSU, in-service software upgrade, is really SSO. So if SSO is version 1 synchronized to version 1, then all ISSU is version 1 synchronized to version 2, and then I do an SSO to version 2. Okay? So if you understand SSO, then you actually already understand ISSU. Okay? And I actually had that animation for the question. I don't even remember who it was asked me that question. But if you have single attached clients, and this is particularly at the access layer, the 9400, if you have that, and this is some very important camera, some very important access point, very important heart monitor or robot, then please prefer a 9400. Okay? It is going to cost you more money, but it will save you time later on. Okay? Now, starting with the fix, like I was talking on the previous one, the same SSO and NSF capabilities are available, but these are fixed switches. The important thing here is that I can stack multiple of these fixed switches together. One of the things that I only barely talked about with the SSO and NSF is I was saying it was synchronizing all of those things. Well, when you think of a switch and how it's talking to its neighbors, it's learning MAC addresses, learning ARPs, and those kind of things, that's all software. That's just you and I talking to each other. But that's going to be programmed into the ASIC of the switch. So that's the difference of this distributed data plane. So each of these switches is also forwarding and capable of taking over. Okay? Now, this is a cute picture. Anybody go to my A6 and iOS XE session? At least one or two? Okay, a few of you. So you've already seen this slide. For anyone that has not, it was just a nice visual way to represent the difference of the software being synchronized from the actual hardware programming. So that's the only point of this slide. I like nice visual representations, but it's why it's so important to you. And again, you're trying to convince your finance person, you're trying to convince your management, should I invest in this technology? Worth spending my skill points on this? And the answer is yes, because now everything is synchronized. If that link fails or if that individual stack member fails, it will switch over to the other switch. All right. Oop, too many clicks. Go back one. Okay. I also often say, like, a lot of these slides, and Jakob did mention we have a lot of hidden slides. I did confirm, Jakob, that the slides are posted. So there's actually many more information that you guys can check out. But you're going to forget most of these slides. But there are 1 or 2 or 3 slides that I want you to remember. This is one of those slides I would like you to remember. And what it's asking you is, neither of these are wrong. In fact, I will tell you scenarios in which an equal cost multipath design is superior, or where a stacking design is superior, okay? But what I'm trying to illustrate from a min-maxing perspective are the ugly yellow, right? You guys remember ugly yellow from Jakob's section. If you do it in an equal cost multipath design, you are relying on the physical hardware and then the protocol to make that decision. You're relying on the network to make that decision, okay? And what it means is, and I'm using, by the way, equal cost multipath in a general sense. It is actually a term for layer 3, but even spanning tree has a term called path cost, right? And based on how many, so I have equal cost multiple paths, right? Layer 2, layer 3. But in these individual links, I have to keep track of everybody. It's me forming a relationship with everyone in this room. And I have to keep this in my head, right? And then the protocol, whatever that is, spanning tree OSPF, whatever that protocol is what's going to be how fast I can make that decision, how I can change. If a link fails, I have to recalculate, I have to talk to all you people, and then I need to send it over another link, right? So this tends to be in seconds. You might have used the suggestion to use bidirectional forwarding detection, but it's still the protocol that's making this decision, right? And then compare that with Stackwise, the real value you're getting out of it, because they're pretending to be one single device. I am just forming a single relationship with you, and I'm using Ether channel to do that, okay? So I've reduced the number of devices that I'm responsible for. I've put you into little groups, and now I can just think of you as one group. And then when I make a calculation, it's just a Ether channel calculation, right? So decide where do you want to spend your skill points, okay? And again, the operational expense piece of it, because it's not only when things fail, but even just day-to-day operations. So I want to keep track of more individual switches, and I have to manage those, or a fewer number of switches, and I have less to manage. Now, like I said, I'm not going to take a religious position on one versus the other. Equal cost multipath is stable. It's well understood. We've been doing it for 40 years. So there's nothing wrong with equal cost multipath. But it means more devices. It means more links. It means more CPU, more DRAM, more fib entries. The size of the device that you chose, from a simple device may need to have a larger TCAM table now to support your ECMP design, okay? Now moving on to stacking. Would anyone go to my stacking session, particularly the next gen stacking? Okay, quite a few of you got to that one. So you've seen these slides before too. In the traditional stacking, all that's really important from this slide is that these 8 switches form together to become one logical switch. So what was traditionally 8 different IP addresses, 8 different configurations, 8 different spanning tree neighbors, I have now turned that into one, okay? And in the little diagram at the bottom, they appear as a single device. So when I talked about not relying on the protocol to make that decision, it just appears as though it's one device with multiple links. And it doesn't have to reconverge and take a very long time for your network to fix itself, okay? The most important thing about stacking, the whole concept of stacking, is Ether channels, okay? Obviously, I can put multiple members together, the whole save IP addresses thing. But from the networking perspective, the thing that is going to min-max your network is multi-chassis Ether channel, okay? Now, this is, again, you'll recognize the tag in the top. So this is in Jakob's 1500. So I'm going to do the similar thing of just kind of speeding up a little bit. In the access layer example, all I want to do is I want to collapse all those really complicated access layers. And One thing talking about diagrams, oftentimes you'll see a diagram and it's a rectangle, core, distribution, access in a rectangle. It's like, no, that's not how we build networks. We build triangles, gigantic triangles. And for every, 2 core switches, there are 100 or 1,000 access layer switches. Okay, so that's what you're trying to do, is simplify that 1,000 access layer switches. Now, it has the same characteristics of any access layer. So all the things that Jakob talked about keeping track of your MAC addresses, keeping track of layer 2 VLANs, and so forth. But now I'm using SSO to keep track of that. So again, I don't have to do any manual configuration to manipulate that. For example, if I had all those 100 or 1,000 access layer switches, it means lots of VLANs, lots of spanning tree. It's just a single switch, so I don't have to worry about spanning tree anymore. So in that way, I have maximized my access layer. Now moving on to Stepwise Virtual. This is now your core or your distribution layer, okay? And it has the same physical design, so everything you learned from Jakob about core distribution access and the physical cabling behind it is still true here. But just like the access layer stacking, what I'm doing is I'm combining those core switches or those distribution switches into one, okay? Now, if you think about what it means to be a distribution, if you were looking at his slides, he talked about things like first hop redundancy, so things like HSRP, VRRP, and so on. And normally if you have a layer 2 access, this is also your spanning tree root. So you have all these different protocols, and they're all collapsing on the distribution layer, which makes the distribution layer the most critical point, right? And again, the magic of this is the multi-chassis ether channel, okay? So even though the physical design has not changed, this is a traditional design. My distribution layer runs some kind of first hop routing, and they pretend to be the same router IP, the same MAC address. But then spanning tree is going to block one of those, because this is now a triangle. You're creating a loop at layer 2, right? And even though the same physical setup, the same number of cables, same number of switches, this distribution switch becomes one logical device, and those links that were at one time blocked because of spanning tree now become just a single interface using ether channel. So from that picture to this picture, okay, that's what is going to help you maximize your distribution layer, okay? Now, seeing these basic slides, the real point here, again, like the access layer stacking, is to reduce the number of neighbors that you're dealing with and reduce the number of protocols that you're dealing with, okay? They still are distribution layer switches, so you will still have those, but I will significantly reduce the number of OSPF or BGP peers that I have. I become the spanning tree root. There's only one single VLAN. There's not multiple VLANs that have to be synchronized between them, and so on. Okay? And again, using that SSO, and instead of, normally what I say, if you understand a supervisor and a standby supervisor in a modular chassis, it's the same thing. I've just moved the standby supervisor to that second chassis. That's it, truly. Okay? One thing, that last one, because it went by very fast. One thing about stacking, this is the other key consideration in min-maxing. I used to have MAC addresses on these 2 different switches. They're kind of actually like split between the 2 different switches. All the good things of combining them together does mean those 2 sets of tables are now maintained by this one single system. So it does mean that it's going to have more MAC addresses, more ARP entries. Okay. Now, for those of you who raised your hand, went to my session, beginning with these new 9350 and 9610, this latest generation of smart switches. We've also introduced a brand new stacking architecture. I'm not going to do the vol-long version like I had done in the other one, but if you went to that session, I said, this one slide is all you really need to know. You didn't even have to attend my session if you memorized this one slide. Previously, that ring stacking technology, as well as the stackwise virtual between the distribution, was a completely proprietary. Cisco made it, and you couldn't use it any other way. And we put our own little special packet headers on there, right, to get it around. Beginning with this new architecture, it is ISIS. If you're familiar with that, it's a standard layer 3 routing protocol capable of doing layer 2. But most importantly, shortest path first. So I'm no longer restricted to a ring topology. It's a point-to-point architecture. It means intermediate system to intermediate system. And I'm using a standard VXLAN encapsulation to do it. Now, the other thing it says there, if you're familiar with how the operating system works, it's a Linux multi-threaded architecture. And it says a new bootstrap process and cluster process manager, whatever. If you know what Linux and having different processes means, is even if iOS dies, the cluster manager is still online. So if you think about that for things like software upgrades for HA and those kind of things, that's a huge, huge difference. Before it was all just bundled into iOS, right? You would try to do some changes and you try to like load the new software. That's why you would have challenges with ISSU, right? But by having this now as a completely separate thread, it's much more stable and it makes it easier to upgrade, okay? Lastly, it is common between the 9350 and the 9610. Before 9300, 9600, two totally different protocols. We called them stackwise, but they were completely different things. This is now the exact same architecture whether you have a 9350 or you have a 9610. Okay? And then all future C9K will use this new smart stacking in GSVL. Okay? I have a long slide, and now I kind of regret putting it. People who went to my session got it, but it was just a visual representation, like the high availability slide I showed you earlier, just to give you a nice visual representation. And the difference being this separate Linux thread. And what I tried to do was make the colors the same, so you can see that the software layers between the bootstrap process and the feature manager in green, the software layer. But if you look at the cluster manager, it actually exists in red at the data plane, right? And it's all hooked into the ASICs. So if you translate all of that, it's like, this cluster manager can completely control the ASICs. It can completely control the system regardless of what happens to iOS. Okay? That's the short version. There's not much to min-max here, so that's why I kind of regret it. I'm like, well, okay, this is more for you to know. You should min-max by trying to use this new 9350. That's the message to get across. And if you are interested, this session is available. So if anybody's curious, just ask me in the room, and I'll make sure you have the slides for that one. Now, getting on to where it does matter is kind of like this slide. Comparing traditional layer 2, layer 3 equal cost versus a stacking design. So in the first one, you don't have to do the math. I did the math for you. It's even in the speaker notes. But you can count there are 19 independent switches, depending on whether we're talking about the access layer, we're talking about distribution core. It's going to add up to this many individual speakers in adjacency. So again, this is neighbor relationship. Everybody's done show IP OSPF neighbor. How many neighbors do I have to keep track of? That translates to CPU and DRAM. How big is my routing table, and so on, right? And again, the failure is based on the protocol. Okay, so however good you've done it, is it tuned? Is it optimized? But then the exact same physical design, from a stacking perspective, I've cut that in half. I went from 19 nodes to 8 nodes, and the number of adjacencies went down significantly, and the failure is based on multi-chassis ether channel. Okay, so again, it's investing in capex versus investing in opex. Okay. Like I said, there is that session, so there's even a link in there. I'm glad I added that slide. Okay, so you get the point. This is an interesting thing from design best practices. Utilize that ether channel. And what it's trying to show you, even though it's a stackwise virtual, they're still single attaching them. They're not actually utilizing that multi-chassis ether channel. You should always want to dual home. So whenever you have that opportunity, because again, OpEx versus CapEx, you are going to save yourself time. Your network will converge if you invest in the extra cabling and utilizing ether channel. All right. Now, I wanted to close out this section as I go into the next section. And I'm actually introducing a bit of the next section on this slide, but it was the only place I could really get it. So on the traditional is the first hop routing protocol. By the way, that's like a term that refers to HSRP and VRRP. But the point is that it's spanning tree on the south side, on the layer 2 side, and that's going to cause something to block, and you're not utilizing. And all it does is pretend to be the IP gateway, and then you do traditional routing on the top, equal cost multipath, right? Now, we just talked about Stackwise Virtual, so you understand that. The difference is that I don't need any longer that blocking. It's an ether channel, so all ports are forwarding. Another aspect is a multi-chassis ether channel also works for layer 3. So my north side, like OSPF neighbor, BGP neighbor, gets the same benefit. I don't need multiple neighbors. I just have one neighbor on the port channel, okay? What we are also introducing is BGP EVPN multi-homing, okay? It has a few names, MLAG, you might have heard ESI. If any of you have used Nexus in the old days, there's a similar technology called VPC. But the point is the same. And it's really very much in the middle. What I'll try to do is I will make a layer 2 ether channel, at least from the access layer to the distribution. So I gain the benefits of that multi-chassis link aggregation. But they still remain as 2 independent boxes. Okay, and it's utilizing, I said I'm going for my next section, it's a fabric-based technology. So EVPN is creating this multi-chassis link aggregation, okay? The other key thing to call out is kind of the north side. So this multi-homing is very specific to layer 2 port channels, okay? It is not available for layer 3 port channels. And the thing to really remember is this is all of these are available depending on what your network design is. There is a dedicated session on HA, so if that's interesting, please check that out. So moving on to virtual networking, okay? Now, again, I've used this term because I want to emphasize the virtualized part of it, okay? There's specific technologies I'm going to talk about, MPLS, Lisp, and EVPN, but these are all virtual networking technologies. Now, another term you'll hear a lot is the overlay. Whatever, you'll hear underlay, overlay. What you really want to do, what I want to do from a min-max perspective is I want to take away complexity, and I want my network to just be simple. Has everyone heard keep it simple, stupid? KISS? Okay. That should be your number one min-max objective. Keep it simple, stupid. Having said that, my customers, my users, your users are continuously trying to add new features, new services. So what I wish I could do is I could keep it simple, stupid, but have something else that gave me where I would put my features and put my special features, right? So all it is we have other names like tunnels and virtual networks. So what I'm doing is I'm creating just simply a logical topology on top of my physical infrastructure. That's the nature of virtual networking, okay? And particularly from a min-max perspective, this enables a whole bunch of things like layer 2 overlay. Why do we build VLANs? We build VLANs because our super important application from like 15 years ago still uses broadcast. Anybody have that same broadcast application that's very important for their company? Okay, I expect almost everyone to raise their hand. But do you love VLANs? Those same people, do you love VLANs? Do you love spanning tree? Okay, well, he does. We'll check with you later, man. The point is, I must, as a network designer, provide these layer 2 services, but I do not like VLANs. I do not like spanning tree, but I must provide the service. This gives you a way to give them layer 2 subnets without spanning tree, okay? And keep the network simple, the actual physical topology. Other examples you hear a lot is the segmentation. By the way, VLAN is a form of segmentation, but in particular, like layer 3 VRFs, VPNs. Okay, so I wish there was a way for my company I could give you this natural security capability without a bunch of complex things running VRFs and VPNs and stuff. So by running this overlay, I can create these segments, which are actually VRFs, but I don't need to worry about VRFs or any complex thing like that. Okay. Now, so the important thing is it's just a logical virtual topology that runs on top of your physical infrastructure. And on the physical, it's keep it simple. As long as I can get from point A to point B, that's all I need to know. Basic IP routing from the access layer switch to the core switch. Keep it simple and don't ever touch it again. Okay? There are entire books on this. There are entire sessions on this. And I have those links if you guys are interested in that. So again, this is not the master fabric class. It's the min-max. Why is that going to... this will truly maximize your network. If you are not looking at fabrics, you are hurting yourself. You are minimizing your network. This is a very, very easy way to maximize your network. Okay? So I'd love to talk through each one of these at their best, but that's the key message, to use fabrics to maximize and provide the additional services. Now, there are many different options out there. You say, why do you have MPLS there? Who here is using MPLS or has used MPLS in the past? Okay. MPLS is an overlay technology. It was the first to introduce VPNs, and particularly L2 VPN, L3 VPN. And if you think about it, that makes it the first fabric. Okay, why did we build MPLS networks? Oh, because I had this one area, this campus network, and I had another campus network, and I just wanted to connect those two campuses together and be able to stitch my VLANs across. L2 VPN. Okay, that's still true. And if you're still using MPLS, that's okay. Keep doing that. Okay. However, in the years since, we have introduced these new technologies doing the exact same thing. So anyone that did not raise their hand, they may wish they could have done MPLS, but I didn't want to learn this BGP, multi-protocol stuff. We now have new technologies that do the same thing. Okay, they will create an overlay network with you. One thing I should have said is the encapsulation. Just like a GRE tunnel, what I do is I take that original packet and I'll just put another thing on top. And I said from point A to point B. What I'm doing is that outside packet is just saying get it from point A to point B. And as it goes through, it's only looking at that encapsulated packet. Finally gets to point B, takes that off, and now it's back to the original packet. So that's what tunneling across is, right? All three of these are encapsulated tunneling technologies, okay? Now, where it matters, and by the way, I'm using the traditional EVPN example. If you're familiar with Cisco VPN, EVPN, we have enhanced it to be much more similar to Lisp, okay? But what's important, again, is the ugly yellow, okay? So if I had MPLS, I did have L2 and L3 that gave me virtual private networks, but really they're based on layer 3, and you would have to map all these VRFs, do multi-protocol, and map those to MPLS labels. It's cool if you know what you're doing. Now, as you get into EVPN, they call them virtual network instances, whatever, right? It's a VRF, okay? And all it really means is I'm putting certain routes in this table, different routes in this table, different routes in those tables, and they've become segmented, right? But traditional EVPN really is seeking to do just the layer 2 piece of it. So it was the Ethernet VPN. Normally I would put the letters BGP in front of it. This is a BGP, is a function of multi-protocol BGP. Okay? But it gives you all those advantages. What's really important is utilizing VXLAN encapsulation, okay? And switching from MPLS labels to VXLAN, okay? VXLAN, if you're not familiar with it, is a virtual extensible LAN. Why do I care? It let me carry Ethernet headers. So when you think of Ethernet, what I want to keep the MAC addresses and those kind of things, right? So by switching to EVPN, I just automatically get layer 2 and layer 3. I didn't, in the MPLS case, I said L2 VPN. There's another protocol called VPLS, Virtual Private LAN Services, which is actually kind of MPLS, but it's actually separated. EVPN has these both automatically inside of it. So you went from 2 different protocols to just one, okay? Now, Lisp, again, this is not the master class, but the difference is a mapping system. And it provided what we added for the first time with Lisp and software-defined access was also adding security group tags, SGTs, right? So not only can I carry the layer 2, layer 3 VRF, but I can also now carry this policy tag, right? All right. So these I'll go through, again, we'll go through these pretty quickly because I want to get on to the next sections. But the goal of what I was trying to accomplish is to utilize some encapsulation to create a tunnel over the top. And when you're thinking of your designs, you're thinking of, should I get a box that's capable of MPLS, or should I get a box that's capable of EVPN or Lisp, okay? Now, in the EVPN case, some nodes will be considered the border or the spine. The border is a border. It's how I get to the other place. And the spine, by another name, is a BGP route reflector. So it's going to keep track of where all the routes are for the host. So this is a scale question. I should have added the slides similar to Jakob did. Like, the main thing is the scale. If you're going to choose a device that's going to be your border or spine, you probably want like a 9500, 9600, simply because of the scale that it supports, okay? The other thing you'll notice is that's usually the core of your network. So you already know these things and you're building on top of them. Now I'm just going to put that same core box. He's going to be my EVPN border or spine node, okay? Now, when you look at the leaf, and they change all the names. That's why I was like, okay, this is the access layer switch, okay? Wherever the end of that VXLAN tunnel is, that's the leaf node, okay? And similar kind of things. This is where now the layer 2 from before, the spanning tree, would connect into it, and you would map out your VLANs and these things, okay? So the same rules that Jakob was talking for min and max also now apply to the leaf node. Jakob did make one important point, which was the layer 3 roaded access, okay? Remember I said from point A to point B? So that's the IP address of that switch, right? And if I want my fabric to go all the way to the access layer, that means the access layer is layer 3 routed. That's point A, and then he's going to send it to point B, which is your core switch, okay? But it does mean you need to make it layer 3 routed, so that's something you're going to min-max your access layer. You may want to look at what is required for layer 3 routed access. Otherwise, you get it. Higher scale, he's now dealing with ARP and neighbor discovery. Maybe your L2 access never had to deal with ARP before. He is now a layer 3 routed. SD access follows the same model. They use the same terminology for most. The border, in this case, they call it the control plane node. But this is what's keeping track of all the routes. This is, again, your core switch. And, you know, you'll have to look at the scale to support these number of clients and VRFs. Okay? And then lastly, the exact same thing with software-defined access edge. That's your access layer switch. And it's the same. Both of these are using VXLAN, so it's the exact same thing. This is a layer 3 rooted access. He'll have an IP address. He deals with the VLANs and the ARP. All right, so there are dedicated sessions for this. This is not the masterclass. Please check these out. There's one for EVPN, and there's one for Lisp as well. Okay, and I got to speed up. I'm already looking at my section, and I got to speed up. So the LAN security one's not too hard. In fact, a lot of it is covered. These also have dedicated sessions and an entire security section. But it can't be a single thing. It's not a single feature that you turn on. You need to make sure that security is enabled on all the different layers, whether that's access layer, distribution, core. How does it connect to the firewalls? These types of things. And you will hear a lot about authentication. So all of these new, including the fabric, all of these new security technologies are based on some kind of onboarding. The client comes on, you figure out who this person is or what this device is, you put a tag on them, and then that tag goes with them through the rest of the network, okay? It is the switches that are doing this, okay? Yes, you're talking to ICE, or yes, you're talking to a firewall, but it is the switch that's doing these things. So whenever someone says zero trust access and those kind of things, they're actually talking about the user endpoint authentication, okay? And then using that throughout the rest of the network. So that's where you need to invest your money. If your company is saying that security is a focus for us, it means I may have to spend more money. Furthermore, security team probably has its own budget. So it may come down to, hey, can I use some of your security budget to make the network more security friendly? Okay. I'll go through these pretty quickly. Particularly the endpoint visibility. So this is the authentication, but it's also things like NetFlow and application visibility and control, right? So these are additional features that you can enable on the switch to give more information to ICE. ICE is only as good as the information that you're giving it, okay? And then once I know what that user device is and I've made some kind of tag, now I need to actually carry that tag throughout the network. Originally, we had this in the thing called Cisco TrustSec, but that was a different encapsulation. Now, the whole reason I went into this whole thing about VXLAN and all that stuff, it's carrying the SGT for you. And I said it's a tunnel. It can create it right over the top of your existing network. And why that's going to maximize your investment. Just by enabling a fabric, boom, I automatically have this new TrustSec capability. And I can carry the tag from the access layer to the core. Okay. There's an entire set of things. This is part of the 1500. There's a bunch of hidden slides. But again, I'm just trying to emphasize that it's not one feature. It's all of these features working together. And that's going to play into your min-max decisions. Okay. This one's an important one to know. I'm not going to spend a ton of time on it, but it's an additional thing. It used to be called device tracking. And if you look down in the bottom, it says Lisp and EVPN are SISF clients. So all it means is a IP to MAC address mapping, and I keep track of this table on the access layer switch. So this is additional information that I'm giving to ICE and other security elements, and I can track that host throughout the network. Okay. I already preempted the next slide, talking about TrustSec, but it was moving from IP-based access list to this tag-based access list. That is, in another way, a very simple way to maximize your network. If you're only still doing traditional IP access list, just moving to this Cisco TrustSec model actually makes your life much, much easier. You're not writing old, complex ACLs anymore. So which one do you like? Which one's better? Do you want to write a bunch of IP ACLs, or you just want to write some simple group-to-group SGT ACLs? So there's a full section on that, 2602, and I have 2.5 minutes to do an entire section. Think I can do it? Don't worry, this is not the class to teach you wireless. This is not the class to teach you firewalls. My only job is how to min-max your wired network, your switching network, to work with wireless and firewalls. Now, the important thing about wireless, particularly centralized wireless, I do have some hidden slides on flex and distributed wireless, but I wanted to focus on this one because this is 70-80% of the world. And what it means is I have a wireless LAN controller, or called an edge, Meraki cloud gateway, whatever you want to call it. And it uses a technology called CapWAP. And CapWAP is also a tunnel. It's also an overlay, by the way. But I encapsulate that wireless traffic until it gets up to the wireless LAN controller, and it pops out. Okay, it's cool. It works. This is why it's 70-80% of the world. What it means to me, and I put this little animation, it's layer 2 until it gets to that wireless LAN controller and pops out. Well, when it pops out, the first switch it connects to, that's your distribution layer. That's where your VLAN interface is. So if you think about it, that switch must have enough scale, enough MAC addresses, and enough ARP to support the size of your centralized wireless control. People break this all the time. They buy the cheap switch, and they plug it in up there, and then wireless is broken because we're two different teams and we don't talk together. So ask your wireless team, how many wireless entries are you going to use, and make sure that your switch can support that wireless. Okay. There's other things about wireless high availability, and it's a similar thing. I added this one simply because the difference of two physical links to two separate wireless LAN controllers versus using stackwise virtual. You remember I said stacking puts them together, and then I use multi-chat, the Ethernet channel. That also applies to the wireless LAN controller. He doesn't know that there's two physical switches. He just knows there's one switch with an Ether channel connected to him, which helps your wireless HA. Okay? Lastly, in that fabric, there's also this idea of a SD access wireless or fabric-enabled wireless. This is a single one-hop VXLAN tunnel, and from that tunnel, the data traffic is now put into the switching network, right? So that's the value, is I take away all the complexity from the wireless LAN controller and I do it distributed inside of the fabric, okay? There are dedicated sessions on that. And then firewalls is the same kind of story. You already get it. It's not a masterclass on firewall, but talk to your firewall team because they're going to choose either a layer 2 firewall or a layer 3 firewall, right? And you need to understand, if there's layer 3, there may also be VRFs. So the box that you choose at the core to connect to that firewall needs to understand whether this is layer 2 or layer 3, okay? So with that, I did the same thing about, like, you can equal cost multipath or you can stackwise virtual. You get the same benefits if it's connecting to the firewall. And there are sessions for that. Now, to take us home, some quick reminders. Remember the places in the network and remember the roles and responsibilities. And even if you collapse layers, the role doesn't go away. You've just moved it all to a collapsed box, okay? Always build hierarchical for scalability and fault isolation. There was a bunch of different sections across the 1,500 and 2,500, but make sure you go through this like a checklist. We added this slide, like, did I check this? Did I check this, right? And with that, you're all now Cisco Min-Max champions. Thank you very much. Enjoy the rest of the show.